Okay, Colin's asked me to talk about this project that we are running. It's a collaboration between the University Teaching and Learning Office and the School of AES, Agriculture, Engineering and Science. And we call it the Autoscholar Advisor. So this is a system that connects directly to the UKZN database, and it analyzes student data. So Colin asked me to speak about it because it's a case study of the use of artificial intelligence. It mentions some of the analysis methods and shows you the sorts of results that you can get from it. So yeah, it's about auto-advising staff and students. So maybe to mention that I first started working on something like this when I was at UCT. That was when I was managing a program there, and I realized there were many tasks that could be automated as part of that. So it was just something to save time. And then, of course, it's grown over time to include all these AI methods, and also I found that visualization makes quite a big difference in here. So yeah, it generates advice to program managers, to teaching staff, students, and people trying to support, so the psychologists and so on that might want some insight into the student. And we found that it has a surprising influence on how students behave. So sometimes a simple presentation of the data that the student already knows actually can change their behavior. So in this presentation, I'm talking about the application to curriculum design. So looking at how well the courses hang together, also in particular at this ill-defined thing, which is the progression rate. So we always talk about throughput and progression and so on, but sometimes the definition of that is not completely clear. And so progression, according to this definition anyway, is not the same as passing or failing, because sometimes if you fail a particular course, it has no influence on your curriculum or on your progression. So for example, if it's an elective course, it might not matter to you whether or not you pass or fail that course, because it's not core to the progression of that particular program. Whereas failing a core course, which serves as a prerequisite to many other courses, that might significantly change your progression. So we wanted to identify where there were specific courses which had high failure rates and which could inhibit overall progression. And first, just trying to understand, I have a preference for generalized methods. So I wanted something that could work across any academic program. So a general method that could be applied. But the difficulty was that each curriculum is fundamentally different. And how do you extract features from that so that you could understand how that program was performing? So the first concept was a progression map. So a progression map tries to tell us the number of routes by which students are passing through an academic program. So this is a simple picture of that, where on the y-axis we've got the number of students, and on the x-axis the percentage of program credits passed. And you'll see it's actually for a 5-semester program, which doesn't exist, so it keeps the numbers nice, right? 20%, 40%, and so on. So we are looking at 100 students entering this academic program. And after one semester, right, each edge here represents one semester. So after one semester, that 100 students becomes 70 students that have passed 20% and 30 students that have passed 10%. And so at each stage, you get this kind of fractal effect, right, that the student population splits up into a new branch. So out of these 70 that passed everything, you'll get a certain fraction that also pass everything in the next semester, but a certain other fraction that don't pass everything and pass some other fraction of courses. So if you do this, you then generate a tree of all these possible routes in an academic program. And if we can understand which routes are quite frequent, then we can do some practical things. So for instance, we could look at timetabling differently. So if we knew that many students are failing at this point, then we could developed the timetable so that these students could overcredit in the next semester and they could stay on the minimum time trajectory. So sometimes a simple thing like timetabling can really affect the progression rate. Also, just knowing that that happens there, of course, identifies a point that you need to consider that is this course, is the material at the right level for the students given their preparation from the prior courses, things like that. So there are many applications, of course, if you have a progression map like this. And I was quite wedded to this, right? I was quite chuffed with myself that, I had solved this problem of how to represent any academic program and all its progression routes. But when you threw the data at it, so this is showing an interface from Autoscholar Advisor, so it's reading from the database all these schools and the programs in the school. So if you select a program, then it shows you the progression map there. And so I was crushed to find that you had so many routes, right? You had almost as many progression routes as you had students there. So you see some big spikes. So the majority of students come in with that number of credits, well, 0 credits. You had some transferees that had credits from other things showing up there. And in this particular program, it's actually I should admit, it's a program I teach in the ChemEng program. You can see we are decimating our students, right? So our minimum time students, they almost halve every semester. So you find by the 5th semester that the minimum time students are actually a rarity. So this was a high level of complexity. It wasn't like this nice picture that you could easily find points to address. So the next thing was to say, well, if you have this data, right, this is the same tree represented now as, well, it's actually also a tree. But now you can drill into each progression route and you can look for where the minimum time students had their first stumble. So everyone was on minimum time at some point, right? Even if that was just the first semester. So if you could resort this thing, you could find out what it was that was causing our most successful students to fail onto longer trajectories. And if you do that, then you get a much clearer picture. So it gives you a kind of hit list that these are the courses inhibiting progression in these programs. And so you can identify these major bottlenecks. So you can say these courses are causing our students to no longer be straight through students. So this is an indicator of the challenge to our success here. And of course, if it's in a dashboard like this where anybody can log in and see, okay, this course is actually creating the difficulty, then hopefully it drives some kind of competition here that people try to, but maybe we have a bit too much of that sometimes, the drive for metrics, and Vic actually cautioned us about that in one of the previous sessions, but at least an awareness of which courses may need further support. So currently, people don't really know, right? Maybe if you are teaching in a program, you have a fair sense of what's inhibiting progression. But like I said, it's not such a straightforward thing. You have to know not just what has a high pass or fail rate, but also what is a strong prerequisite for progression. So this does those two things. It figures that out and it tells you your successful students are stumbling in these places. So that was the first application to this. And you see, if you have curriculum structure, so referring to my previous life at UCT when we had the system working, it worked well. We had record highs in graduation rates. We were graduating something like over 100 students from a ChemEng program, which is high, right? It's a program that takes in 100 students. Not that we didn't have recycle, we call it recycle in there, but we had very high graduation rates at some stages. And so those were years when we were using the Autoscholar Advisor, and that was working well because I knew that program, I knew all its rules, and I could hard code them into the system. And of course, if you are dependent on that program, then you will always need somebody to code up the rules of that system. Whereas if you want to generalize this thing and you want it to be applicable to other types of programs, then you need to somehow deduce that curriculum structure. And then I realized that with this tree of data, what you could actually do is sort that data. So you could sort each semester all those combinations of courses that students have passed. If you sort that according to number of credits passed, then if you take the maximum credits passed, that is probably an indication of the minimum time route. So that's one indication. Another indication is the number of students. So in principle, we should have the majority of students trying to pass in minimum time. So you may get that a large number of students translates to a minimum progression route. So when I did that, I got I was able to predict the curriculum. And so this is showing you the courses in the curriculum. So in white, the system is showing us where it has correctly predicted the courses of that curriculum, and highlighted in yellow are where it's got it wrong. So you can see it's incorrectly predicted. Thermodynamics 1, it says it should be a third-year course, when in fact it's in the second year. Thermos 2 should be in, according to it, Thermos 2 should be in the fourth year, whereas it's a third-year course, and so on. And so it's nice to say we've got 92% accuracy, but at the same time, what's the reason that it got it wrong here? So when you look at this data, you find that this course has such an extreme high failure rate. It has a pass rate of 25%, right? And for something like 5 years, this course had a pass rate of 25%. I don't teach that course, but anyway, it had that pass rate. So the system was noting that this course was being passed in the third year only. Right? The majority of students were only passing in the third year. So that's why it thinks it's a third-year course, right? And you see, this is the prerequisite for this other course. So that's the reason most students couldn't take this course, because they hadn't even seen that, they hadn't completed that course. So they couldn't see this course. So that's why it went on to the next year. And that's the same reason for these other courses occurring later on. So you see, these 4 errors are really one error, which is a course that is a major gatekeeper to this whole program. So analyzing just the error in the prediction for your curriculum deduction does give you an idea of where these gatekeepers are. Then in terms of what you can do with this curriculum once you have it, sorry, the color hasn't really worked out there, but you can take a student and map their results against that curriculum, and you can't really see the color here, but mainly in blue here, you've got the courses that have been passed, and highlighted in a different color the courses that are yet to be done, or courses that haven't been passed yet. So you can see at a glance where this student is. And if you think about those ERS records, this is much easier to understand if you have a curriculum to map it onto. So that's a simple visualization thing. But the other thing you can do with this is generate advice to students. So we've got this robot system, that red, amber, green system here. And I've added here further advice to the student. So if it looks at the student, it can give you further information. It can look at how that student has been performing and mention to the student here, yes, you've passed a full load, that's great. Here it says specifically you need to pass at least so many credits in the next semester to get back in the green. Then here it says, although you've been rehabilitated, you must continue to operate like this, to keep going, and so on. So you can auto-generate advice like this. You can create scripts that respond to different criteria. So if you have the curriculum object and you have your script, then you can map that. So that's what's called an expert system. It's not a very sophisticated technique. It doesn't have a complicated algorithm. It's simply a rules. You can code up rules into the system to generate advice. Then this one has a bit more analysis. So this is more advice that it's giving to the student, where it's looking at the courses that have been passed and the amount of time that the student has taken to pass. So it's saying to the student, you've taken extra time to complete these courses. That's an extra overall time of so many years. Your study is subsidized by the government. By taking this extra time to complete, you've cost the state and the university an extra so many rand, right? And that's also an estimated loss of earnings to you of so much. So it generates this kind of natural language advice that students seem to take quite seriously. So generating that kind of advice, that's part of it. Then looking at machine learning. So further things you can do with the curriculum object is try to develop a model that will predict the likelihood of a student's success. So either in passing a program or in passing a specific course. So we are interested in developing this predictive model here using biodata and whatever other metrics are available. So the first step to that was first to look at the curriculum and understand how well everything is hanging together. So this matrix is showing us here along this, well, down this column, these are the courses in the first year in this academic program. And then across here, we've got in the second year. So the interest is how well do these courses cross-correlate? So if it's a subject that has a lot to do with this other subject, then doing well or doing poorly in this course should translate to doing well or doing poorly in this other one. So this number is the Pearson R coefficient. So a value of 1 means a perfect correlation. A value of 0 it's very uncorrelated. And moderately good correlations are considered to be around 0.45 to say 0.6. So I've highlighted those with the yellow over here. And if you look at these courses, here's our Chem-Eng 1, Introduction to Chemical Engineering here. If you look across here, this correlates with nothing, right? It's not introducing anything about chemical engineering. It doesn't correlate at all with our second year courses. Whereas this course, physics, right, which people are routinely talking about dropping, they're saying, why do engineers need to know about relativity theory, right? So people are talking about dropping this, but look at this, you've got high correlations here. So that probably means it serves an important foundational role in these courses. Well, Vic will talk to causality a bit later, right? So with this matrix, we can understand how our curriculum, how cohesive is it, how well is the knowledge transferring from the one place to the other. And then if you have these indications of good correlations, you can think about developing a predictive model for this. So here's a simple set of data where I'm trying to challenge the algorithm. So this is now moving on to machine learning, which is a subset of artificial intelligence. So in machine learning, it is about taking data and finding patterns and learning something from there. So here we are trying to predict this course, Reactors 3, given results in Reactors 2, Maths 1, Economics, and Psychology. And so we've got the data in a partitioned form, which means we take the continuum of numbers. So we know we get all these real numbers, well, not integer numbers, we get integers for the students' results, and then you can partition them. So you can say, okay, that number is actually a pass-fail, and that number is between 0 and 30, and so on. So it's necessary to do that, to simplify the number of groups that you have. But here's the data where we've got pass-fail data. So we've got a data set where these students have either passed or failed, and they've got some other range of marks in these other courses. Right? And you can see it's not that easy to fit this data, because if you look at the fails here, you've got a variety of other results in these other courses. Among the passes, you've got a variety of responses to that. So it's not that easy to fit this data. But what the algorithm does, this is the classification or identification trees. So if you run an identification tree on this, you'll find this logic package is the result. And if we draw that graphically, it's saying if you want to predict your reactors 3 result, first check reactors 2. If you have results in this low range, you'll likely fail. If you have results in that high range, you'll likely pass. If you have results in this middle range, then it's not enough to look at just that course. You also have to look at the Maths 1 result. And if you are in that range, and if you pass that first time, you'll likely pass, and so on. So this logic package completely captures all that data. So you can regard this as a model now that you can use to predict the likelihood of someone's success or failure. It says here also, these courses don't correlate well. So it works out first, what is the strongest indicators of success in this course. So that's what this aspect of machine learning does. Identification trees, it helps you with, we had introduced that term earlier, factor analysis, where you look for which variables most strongly influence your outcome. So that's an example of AI. This is just some other stats that you can generate from the data in the database. So this is looking at, on the PostGRAD side, the mean residence time, right? Mean residence time, how long are you staying in the system? So for master's students, if you look at the graduates of if you look at our graduates, the masters are there on average, you can see around 2.4. So they are taking about 2.4 years to complete. But if you look at all the students, if you don't just look at the graduates, if you look at all students, the average is more like 4.5. So that difference straight away tells you we are losing many, many of our master's students. So that's a highlight that in this academic program or in this school, your loss of postgrads is quite high. The dropout rate is high. So you can do that with, you can do the same exercise with PhD numbers and so on. You can also look at staff and how many postgrad students they're supervising. So in this school, we have 11 staff that have 0 postgrads, 27 staff with just 1 postgrad. So that's an indication that there is capacity for this school to really increase in terms of its postgrad numbers. Yeah, I think that's enough. So that's just a quick introduction to some of the kinds of analysis that you can do. Okay. Any questions or comments on that? Maybe I should say the Autoscholar system is, as I said, it's in AES at the moment. It's in alpha testing. We will be looking at rollout to other colleges as we develop it. So in case you're interested in getting access to that.
Instead of considering the courses to predict the outcome of the program, can we try to use maybe other information like gender, age instead of the courses? Because I'm actually trying to see if I can use those other ones, not the actual code, the marks each student got for a particular course. But probably
for sure.
And the metric marks, the grade, and so on, and probably. But actually, here I have the output I have here would consist of the credits. Then I want to see there's a number of credits that each student needs to complete before you get a degree at the end of the year of your program. Some people will get that credit, but some people will probably take 1 more year. Some people will repeat some of the credit and still fail some of the credit. So basically, for those that, I want to see if it's possible for those that have, to classify those that have finished in time with those that do not finish in time.
Yeah.
How am I going to use these variables to predict if a student will probably finish within the 3 years, or he will take maybe 4 years, but within the 4th year, he's going to probably pass a course or still fail the extra credit. So basically, I'm trying to find out how can I'm actually trying to use a machine learning approach, not a data analysis method. So I'll try to figure out which method is appropriate. maybe.
In fact, that's what we're currently doing. So this is showing some other studies that we've done here, where you can choose your input variables. So it looks at the database and it just reads all the variables that are in the tables pertaining to students. So it looks at what biographical information, what other information is available. So there are things like fee balances, right? Decision codes. Ravi was interested in, is this self-fulfilling prophecy that if you are predicting, if you are saying that the student is on orange, does that now become the thing you stick at, or is it what we intend, which is that you try to get out of it?
The robot system was designed to be an early warning system to prevent students from either dropping out or being excluded. Now, if you're on green, you're okay. You're on the freeway. If you fall into orange, you are at risk. Now, what we are finding is that the possibility of rehabilitating from orange to green is very, very low. Which means the system is not doing what it's intended to do. So we need to find nuances in, tracking students' progression and making available data of successful students and how they navigate the curriculum. For too long have we spent our energy and resources on tracking at-risk students, on students who fail, and that kind of analysis doesn't reveal much about successful pathways. So Randhir's system is able now to say, of a class of 100 of engineering students, this is the pathway that the most successful students have chosen. So going back to the point about the robot system, we're conducting a study. We've commissioned a team to look at the phenomenon of rehabilitation from orange to green, and we'd like you to be part of that, to do a critical analysis, because if the system's working against the student, we need to revisit it.
I'm particularly intrigued by this data because this then talks to the kind of questions I myself am asking about our own curriculum. And in particular, I'm concerned about whilst the system then can predict modules that are underperforming in terms of pass rates, I'm wondering, can we go a step further and predict what are the indicators for risk? Do you see what I'm saying? So, actually entering that module. But there must be, I'm just wondering what within that module, or how then can we predict the risk, rather than saying the student is at risk already, but what then are the predictors for risk?
You do have all this data available. So the gender, the quintile school, the matric results, the fee balances, that might be creating stress and affecting studies. What were the other things? There's actually quite a lot of data that's collected there. So for sure, you can correlate those things and look for indicators. And in fact, there's so much there that you could open this thing up. That's what we want to do, to open this up and ask people to go ahead and find the correlations. So it is possible to access this data and go in and look for these patterns.
I think Sabila's question relates to what happens in the absence of this. This data emerges as a student engages the curriculum. But you need sort of baseline information when the student enters. Now currently, there are tests such as the National Benchmarking Test, which claims to do that. Regrettably, that test is not used widely. It's used by UCT, WITS, and Stellenbosch, and possibly UP. We don't use it. We don't use it because in the early days, it had several cultural biases that didn't predict accurately. So what we've done last year is commissioned a new instrument. An instrument that, using biographical input data, including quintile ranking, socioeconomic status, etc., and metric points, and a built-in sort of aptitude, if you like, I don't like that word, test. And that instrument will give you a profile rather than an indicator to help you place the student. It's not an entry mechanism. It's a diagnostic placement mechanism. It will tell you what sort of support this category of student will require for what period of time.
The one issue with all of these things is when you find out when you find out factors that are correlated with stop out or risk factors, is you don't necessarily know why. And even if you get other information, okay, gender is related to success, so I will have these people do a sex change operation and then they will do better. It's understanding what you could actually do about it. And there's kind of two ways you can approach that. One is you study the mechanism. You try, you do analyses to investigate whether this, that, or the other is the cause, and we'll talk about that with causality. Or you do what they do in a lot of times in medical school, in the medical profession. You sort of guess. Take your best guess, try it, see if it works, it doesn't work. Try another thing, and eventually you'll stumble upon things that work. You won't necessarily know why it works, but you'll know it works, and this is, most of our medications come out of this. No, I'm being facetious a little bit, but it's not entirely off the mark. There is a degree to which in clinical research or in teaching and things like that, you just try new approaches, but the important thing is that you try them in the context of assessment. So you try things, you track them, you see whether they work, you see who they work for. So for example, we have an early warning system. The instructors tick off how the student is doing along several dimensions. Information goes to the advisor. Advisor contacts the students because the advisor sees it across the classes, how the student is doing. So they may contact the student and say, hey, why don't you come in, I need to talk to you. Or, hey, I understand you're having some problems with writing. Why don't you go to the writing center? Well, the students who have the biggest problems don't follow up on that. They don't have good help-seeking behavior, so you have to start studying help-seeking behavior. So basically, it gets you closer and closer into the nuances of what's going on, but it gets more and more complicated as you proceed as well. But it does help improve the success rates. And the only other thing I want to comment on, all these things have error. These are behavioral measures, and you can tell a student based on a diagnosis based on previous people what's likely for that student. And then Colin quickly showed the false approved, what language, FAR, FRR, what was your language on that? False acceptance rate? Yeah, so the true positives, the true false positives, the true negatives, the false negatives. These things generally don't have high amounts of precision when you're dealing with behavioral data in education. Not like in medicine, although medicine, it depends what you're looking at. If you're looking at drug behaviors, it's one thing. If you're looking at people behaviors, it's just like higher education. So sort of sentencing a person to their fate based on previous people like them is not something you should do without knowing, without being trained in things like counseling. And so we really have to become a lot better at understanding how to use this information. Otherwise, it won't make a difference.
We have some data where you can regard it as training data, right? So you've got a data set where things have already happened. So, and you do have to have an outcome so that you can create your logic or your model or whatever it is. So that's your training data. Then once you have a model from that, then in principle you can predict how the next student could respond. Of course, with human beings, it's much more difficult. I mean, with chemicals, it's easy. They behave quite consistently. But human beings, there are many more variables, and it's quite difficult to model. So it's an ongoing process. You may have also changes in the environment. So sometimes the lecturer will change on the course, and that may have a significant influence. So all those factors are there, but if it relates to the variables that you've investigated, and if your model is fundamental enough, then it can have predictive capacity.
Yes, I thought it was quite interesting when you presented that map of your various courses and then identified, was it one of your physics modules was the one that was being the sticking point? Am I right? Theoretical physics was coming up?
It was correlating well with our other courses, so it looks like it's a good foundational.
Yeah. So I think that particularly, I think, is quite interesting to be known across the board, like which is the course in each program that needs the resources put to it for progression. Because although I don't have that in a statistical frame at the moment, but I can certainly in my own program identify which course that is. It would be very interesting to see if it flagged up like this in a real analysis. And then saying, you know, as we've just been speaking about, how does one gear in before?
Yes.
You know, so if you know that's the course and your entire program, that's the one, so to speak.
Yeah, that's
changing
exactly.
our behaviors for that.
Quite a lot of the time you'll find curriculum development and so on going according to people's bias and their belief of what's going on. Whereas once you have the data, then you really have a strong backing to take action. So for sure that thermodynamics issue, that was something that I was actually very emotional about and very... then finally, when I did this, I said, "Oh, finally, I have this is the backing to say yes, we have to do this." So, it is about supporting. You can say part of this is about advocacy. So, being able to say that yes, there is this influence, and is it significant or not? So that's another question. What's the significance of this correlation? So if it's strong enough, then you can say, yes, that justifies taking action here rather than there. So sometimes it's about, quite often people talk about strategy and it's just about we must be the best program, whereas real strategy is we have a finite set of resources and we can allocate them to doing only so many things. So like I showed earlier, that table where it's prioritized the courses that are limiting success to the greatest degree, that gives you a priority list of actions.